Hi, I'm Pat Bilchin. I'm the Director of Analytics and Data Services at Perspecta, and I'm here today to tell you about some of the AI challenges for adoption at scale. First thing I'd like to introduce you to is a concept called statistical machine learning. This is the dominant way that many AI models are done today. It's a very popular approach to making AI models based on complex regression of data. And one of the questions that comes up here is how accurate are these approaches? And in one example that's shown here, this is an example of an algorithm developed for DARPA where they looked at building algorithms that could do scene understanding and description. And here it says, a baby is holding a baseball bat. Now when you look at this, you go like, it's kind of close, but it's not really correct. And that is one of the main challenges we see now, where it's the phrase that DARPA likes to use is statistically impressive, but individually unreliable. You can always find a couple examples that give you unease about how the algorithm is performing. Now, AI generally performs well on easy problems, but in most problem domains, all the problems are hard. In this example, this uses pre-trained imagery from a very large data set called ImageNet. And if you look at the top of this image, these are the easy classes. These are things like a tiger, where the tiger has very discrete features. But then in the bottom, these are the classes that are the hardest. One of them is a hook, and the image that's shown is like a hook at the end of a piece of construction equipment, not like a Captain Hook hook or a fish hook. And so objects that are more ambiguous are much harder to recognize. This is a big challenge in especially the defense, intelligence, and healthcare domains, because most of the stuff you're looking for is actually really hard to recognize against the background. And so when we see examples of, hey, the computer wins the video game, or it can tell dogs and cats apart, that's usually not the problem that we're trying to solve. Here are some additional examples of hard problems. One of my personal favorites is called Muffin or Chihuahua. This grid shows images of muffins and Chihuahua heads. And as you can see, some of them actually look pretty darn close. Like the one I put the red box around, you go, boy, that really looks like a sarcastic Chihuahua. This is an example of what's called a low contrast problem. The examples are actually not that different from each other. And a human is pretty good at detecting the nuance, but it's very difficult to train a computer to tell the difference. In the middle example, these are a pair of researchers that built what's called a patch attack. So there's a common person detector algorithm that will draw a box around a person, and they used a technique called adversarial machine learning to design a patch that is the opposite of a person. It basically is detected by the computer as having an object score of 0. When you print out that patch and hang it around your neck, your object score goes to 0, and essentially you're invisible to the algorithm. This represents a new type of stealth technology, or an invisibility cloak, to hide you from these algorithms. And the third example I'll show you is what's called explainable AI. In this example, an algorithm was used to differentiate between a husky and a wolf. And then when you ask the algorithm, why did you think that was a wolf? It says, because of this. And the thing it points to is the background. And it turns out that the wolves were often photographed in front of snow, and the huskies were photographed in front of grass or dirt. And the key feature the computer found was actually the background, not the animal. And so when you're training these algorithms, you have to be very careful that you don't set up the problem incorrectly. Another phenomenon is called giraffing. Here, there are 3 pictures of giraffes, except the pictures aren't actually giraffes. These pictures have been labeled as containing a giraffe from a machine learning algorithm, but they're not in there. Okay, what's really going on? It turns out that giraffes are very rare. And if you ever saw one, you would take a picture of it with your camera, and you would probably post it on the internet and say, hey, cool, it's a giraffe. But those pictures are usually also nature scenes or large open plains in Africa that have grass and maybe a couple cool-looking trees around. So it turns out that giraffes are very overrepresented in image data sets. There's just a lot of giraffes in there. And if you train your algorithm based on publicly available imagery, you're going to have a lot of false alarms that are related to this phenomenon. That's an example of an object that is overrepresented in training sets. Another example that was popularized this spring is almost every AI researcher got their hands on a bunch of COVID chest x-rays, and they ran through an algorithm to say, hey, I can build a COVID chest x-ray detector using machine learning. So this is an example of one such tool that's online where you can upload the picture of an X-ray and it'll tell you how confident it is. In this case, it says the X-ray shown is COVID-19 with a 99.97% confidence. Well, unfortunately, these algorithms are very biased towards the training data and they tend to have a high false alarm rate. You know what I did when I saw this, right? I uploaded a picture of our friendly giraffe and just to see, hey, what would the algorithm say? And because of the way that it's trained, it says, hey, this picture, actually a giraffe, is a COVID positive chest X-ray with a 99.82% confidence. Poor giraffe. So you can't always trust these examples when they're looking at training data sets. They may be biased toward a certain type of sample. Now, the primary flaw in the examples I've shown is the selection of training data. This chart shows the way that training data is typically distributed. In this case, I mentioned the ImageNet data set up front. The ImageNet data set has about 1 million images in it. So if you divide your images into 80%, 15%, and 5% for the training data, the validation data, and the test data respectively, which is the rule of thumb that you would use, it turns out that rare events almost never happen in the data. You have about 3 Six Sigma or very rare events in your training set. So your algorithm only saw very rare things a couple of times. And your validation and test set actually contain less than 1. So you can't evaluate how well your algorithm does rare things. And so I use this to pose the question, should we really be using these essentially Gaussian distributions of training data where you have many things that are common and are at the median and not a lot of rare examples, or should we be biasing our training data towards the weird stuff, towards the things that you don't see very often? And I use this example in military and intelligence domains because if there's a war, we're almost certainly to see things in the tails that we've never seen before. And when you talk about rare diseases, you're always operating in the tails. And when you're talking about clever fraudsters, they're always hiding in the tails. And so be careful that you're not using normally distributed data when your problem isn't really like that. Now, one of the things in building up trust in machine learning algorithms is assessing the results and seeing how they do in real-world problems. This is an example of an algorithm that my team built to participate in a large competition of satellite imagery data. So just like ImageNet that had about 1 million ground-based images, this data set has about 1 million images of common objects, things like planes, ships, buildings, etc. But the problem is there's a ton of variability across the classes. For example, a plane might look like a Boeing 767 that's a large passenger aircraft, but that same class of plane also encompasses little things like Cessnas and F-16s and a bunch of military equipment as well. Buildings are all different sizes and they look different in different parts of the world. Some of the cars are actually parking lots that were mislabeled as car. So all of these things influence the accuracy of the algorithm. And as shown here on the chart, when I work with imagery analysts and show them this example, they always go to this plane right in the middle. And they go, in this example, the algorithm is putting a box around the things it's detected with a confidence. And they say, why does it put a box around this plane with a 99.9% confidence, but this almost identical plane in the middle is completely missed? And it's very hard for us to explain why the algorithm is doing that and why it missed so many detections in the image. And this is not very helpful when you're trying to build up confidence that the algorithm can be used to augment what the analysts are doing today. Now, we always say that more data is better, right? I train it with more data. That would be better. But there's a new challenge that has emerged here is that most of the data is labeled by humans. But we also know that humans tire when they do menial, tedious tasks like labeling training data for 10 hours a day. So my team set out to look at what happens if they mislabel the data as they get tired. We intentionally mislabeled some of the data in a data set called PlanesNet. And remember that planes, because they're large objects against a high contrast background, they're almost always detected easily. So this is pretty much the easiest problem that you could have. We mislabeled some planes as not a plane and fed it to the algorithm to see how it would do. We thought that if we mislabeled about 2% of the data, the error rate should go up by about 2%. But we actually found out that there was a very large change. In this case, the deviation percentage was much greater than what we put in. The algorithm was getting confused very quickly by the mislabeled images. And this doesn't give us a lot of confidence that very large human-labeled data sets are going to be accurate to produce highly accurate models in very serious conditions. Another phenomenon that we examined is the variability of slight input variation. This is an example that's done by some researchers at Auburn, where they took the ImageNet data set and they performed some transformations where they essentially generated a 3D model of the objects in the image set and they rotated it. So while the most popular pre-trained image recognition algorithm in the world is about 99% accurate on fire trucks, if you rotate those fire trucks slightly, the accuracy goes down to about 3%. And this is very concerning. It says the algorithm isn't really very good at recognizing things that are taken off angle. Now, if we think about ImageNet, it's literally a data set of the most perfect pictures you've ever seen. It's like a really good picture of a fire truck and a straight-on picture of a cheetah. No shadows, no obscurations, no double cheetahs, no flipped over fire trucks. And so the algorithm is biased to only learn about what things look like under optimum conditions. In another example, the researchers looked at then rotating these different objects and seeing how the classification changed. And the one that's most concerning to me is the one I put a red box around. This is one where you actually have a motor scooter in the scene, but it's misrecognized as a bobsled with an accuracy of 100%. Despite the fact that this is a scene that contains no snow, it's basically like a road in the middle of a city, the algorithm thinks that's a bobsled. This is the opposite problem of the giraffing problem. Bobsleds don't actually occur very often in the real world. It's a pretty rare object. And the fact that the algorithm would guess that this scene is a bobsled and then say it's 100% accurate is extremely concerning. It means that the data set, this model that many people are using for image recognition, is overtrained for a small number of objects that are in the data set and therefore could be guessing the wrong thing if it doesn't get a perfect picture. One of the approaches that can be used to combat some of the common problems in AI training is called fleet learning or auto training. One of the most notable examples of this is the autopilot vision system in the Tesla automobile. The way it works is the cameras and computers are running all the time, whether autopilot's activated or not. And as the human behind the wheel stays between the lines, the computer learns those are lines and he's staying between them. As you avoid obstacles, if the computer thinks certain things are obstacles and you don't run into them, you confirm the computer's bias or belief that those in fact are obstacles to be avoided. So the beauty behind the way Tesla has created their vision system is they built a way to gather data from everyone that's driving the car all the time, and those people will encounter rare situations at the base rate they occur at in the real world. So instead of trying to design a training data set that would give you all the weird stuff that happens, they actually put us all into the training system and allow us to build that data as we're driving. Another very powerful example is a capability that Gmail rolled out called Autocomplete. So as you're typing an email, the algorithms that are running behind the scenes are looking at the context of the email, like for example, to whom is it addressed, or when have you met with them before, and what could the subject be about. The thing I really like is as you're typing, it starts to complete the sentence for you because they have every email that anyone's ever sent through Gmail. And they know what keystrokes you typed before the sentence appeared. So you can build an AI model that says these keystrokes have a certain probability of resulting in this sentence, and that is enhanced by the context of all the other things they know about you and about what else you're saying in the email. So this presents a really interesting way of training the AI algorithms using the data that you have as people are conducting their regular workflows. And this is a very powerful technique that many businesses need to think about how to implement. How can I instrument the work that people are already doing to build AI models that replicate the work that they're doing, building that data automatically and at scale? So finally, just some tips to help with AI adoption. There's a big rush to try to build these models as fast as possible and roll things out, but sometimes they can be met with a lot of skepticism from the users. So we really need the time and space to question the way that we're using the data and the way we're making decisions. We need to train people in probabilistic thinking so that they can better understand when things happen, and the cultural awareness that things happen in different places for different reasons that may be tied to the people that live there. We need both red teams that question assumptions and diverse teams that look at solving the problem in different ways, or else we have a danger of being biased towards falling into a certain preconceived notion of the world that might not be right in all conditions. We need research tools to question the way we've done that, and models that know when they're wrong. A big challenge today is the model can't tell us when it's uncertain about its decisions. AI developers need to not just drink the Kool-Aid that the technology is amazing, they need to be skeptical of the things they've created and how they might go wrong. And finally, you build trust through time. And with continuous adaptation and experimentation, we can build models that people can trust, that can be applied to hard, real-world problems and address some of the challenges I've highlighted today. Thank you.